The word information has become so commonplace that we rarely pause to reflect on what it truly means. For Faggin, however, this term is far more than data traveling through cables or appearing on our screens. Information is an invisible bridge between the reality we observe and the interpretation we give to it. And it is here that the mystery begins. Its etymology, informa, literally to give form, reveals a profound nuance. To inform is not simply to transmit, but to shape the perception of the receiver. And yet, in daily life, we use it in multiple senses: news, instructions, signals, knowledge, as if it were a single, unambiguous concept. But information does not exist in a vacuum. It depends on an observer to recognize it and to interpret it. Here emerges the first enigma. The very same fact can transmit radically different messages to different people. Consider something as simple as raising a thumb. For a foreign tourist, it might appear to be a friendly gesture. For someone from another culture, perhaps even an insult. And for a person who knows the sender intimately, it might hold a private meaning, impossible for an outsider to decipher. This relativity of meaning leads us to a distinction that Faggin highlights: the difference between objective and subjective information. The former relies on a shared and consensual code, the language of traffic signals, for example, while the latter arises from the unique experience and context of each individual. Both coexist in every act of communication, even though we may not always be aware of it. The philosopher Luciano Floridi, a key figure in the philosophy of information, argues that we live in an infosphere, where every interaction is a form of symbolic exchange. For him, information is both a resource and an environment in which we exist. Meanwhile, René Thom, renowned for his catastrophe theory, views information as a shaping force, as real and as active as matter or energy. Even absence can be information. If we agree to meet at 6 o'clock in the town square and one of us does not arrive, that absence speaks for itself. In this sense, no explicit message is required for the observer's mind to construct meaning. Think about the way modern technology amplifies this paradox. A single tweet, stripped of tone and context, can inspire millions or ignite outrage, depending on how it is read. The same image posted online can be a symbol of hope for one community and an insult for another. Even silence, when a message is expected but never comes, speaks volumes in our digital age. Faggin points out that this constant interplay of interpretation reveals a profound truth. Information is never static. It is a living current, flowing between minds, shaped by culture, memory, and expectation. To understand it fully, we must see it not as cold data, but as an ongoing dialogue between consciousness and reality. Faggin insists that this fabric of meanings, both objective and subjective, is the invisible ground upon which all knowledge is built. Without it, neither science nor technology would have solid foundations. But there is a twist. The more we attempt to define information with absolute precision, the more its human and subjective dimension slips away from us. It is like trying to capture a river with your hands. The water escapes, reminding us that the essence of information lies not merely in describing, but in transforming. And perhaps here lies its true power. Information remains alive only while it is being interpreted, while it generates new connections in the mind that receives it. It is not an inert object, but a process that flows, adapts, and mutates. In every conversation, in every shared symbol, lies the possibility of change. Faggin warns that understanding this is not only crucial for science and philosophy, but also for the way we communicate and coexist as a society. After all, if information shapes us, then to understand it is ultimately to understand ourselves. In the 1940s, a young engineer named Claude Shannon transformed our understanding of communication. His goal was not to explain meaning, but to create a way of measuring the amount of information transmitted from one point to another. This strictly mathematical approach gave birth to what we now know as information theory. Shannon discovered that he could describe any message in terms of probabilities. The less likely an event was, the greater the amount of information it carried. In his famous example, letters in English do not appear with equal frequency. The letter E is very common, while the letter Z is rare. That is why receiving a Z in a message adds more statistical information than receiving an E. To quantify this information, Shannon introduced the smallest possible unit, the bit. A bit represents the answer to a yes or no question, such as tossing a coin and getting heads or tails. It does not matter what medium is used, light, electricity, or sound. What matters is that there are two clearly distinguishable states. Here is where Faggin adds his nuance. Although the bit is an abstract concept, in physical reality, it must be implemented with devices capable of maintaining a stable state against noise and uncertainty. In a digital circuit, for example, a bit may be represented by a high voltage or a low voltage, separated by a margin of safety designed to prevent errors. That threshold, invisible to the user, is the silent guardian that preserves the integrity of the message. But, Faggin warns, this perfect form of measurement has a fundamental limitation. It says nothing about meaning. Two messages can contain the same number of bits, and yet one may be trivial, while the other may transform the life of the person receiving it. Shannon's theory excels when it comes to optimizing channels of transmission, but it stops short at the door of human significance. This distinction is essential for grasping that information is not simply a pattern of signals, but a relationship between a symbol and the context in which it is interpreted. The same binary pattern may represent a number, a letter, an image, or a machine command, depending on the prior agreement between sender and receiver. Without that agreement, there is no message at all, only noise. Shannon never intended to solve the mystery of meaning. His genius lay in isolating the quantity of information from everything else. Yet in doing so, he made it clear that the most human part of communication, the act of interpretation, could not be reduced to formulas. For Faggin, this separation is a reminder that mathematical precision, however brilliant, is only a tool. True understanding requires a bridge connecting the objective signals to the subjective universe of the observer. And that bridge, as we will see, becomes far more intricate once it is crossed by living processes. This is why Faggin insists that information theory, powerful though it is, remains incomplete when taken in isolation. It tells us how efficiently data may be transmitted, but not why that data matters, or how it changes the person who receives it. Meaning arises in context, and context is always human, always lived. Without acknowledging this, our models risk describing the shell of communication while missing its heart. To move forward, we must not discard Shannon, but rather complement his legacy with a deeper recognition of the living mind that gives information its purpose. When we think of information, we usually imagine messages, bits, or digital data. But for Faggin, the most sophisticated and mysterious form of information is that which circulates within living organisms. He calls it living information, and its difference from the information processed by machines is radical. It cannot be separated from the matter and energy that embody it. In a computer, software and hardware are distinct entities. In a living being, the program is inscribed into its very physical structure. DNA is the perfect example. It not only contains genetic information, but also forms part of the mechanism that interprets and executes that information. And what is most astonishing is that a large portion of this DNA, for decades dismissed as junk because it does not code for proteins, has been shown to play crucial roles. Modern molecular biology has revealed that it regulates vital processes, controls when genes are switched on or off, and participates in the organism's response to changes in its environment. One of the most striking discoveries in this field is the CRISPR-Cas9 technique, which allows DNA to be edited with a precision once thought impossible. This system was not invented by humans. It was discovered in bacteria, where it functions as a natural defense mechanism against viruses. In this way, nature had been editing its own code for millions of years before we began to imitate it. Faggin emphasizes that this integration between information, matter, and energy is far more efficient than any artificial system we have designed. An extraordinary example is photosynthesis. Plants convert sunlight into chemical energy with an efficiency that, in some cases, approaches 98%, something that our photovoltaic technologies remain far from achieving. Recent studies suggest that quantum phenomena are involved in this process, where particles of light appear to explore multiple paths simultaneously before selecting the most efficient one. These quantum phenomena are not limited to photosynthesis. Emerging research indicates that inside the cell, essential processes such as energy transfer, the detection of magnetic fields, and intracellular communication may involve electron spins, phonons, quantum vibrations within the molecular lattice, and even photons trapped in biological structures. These elements, invisible to the naked eye, may well be fundamental pieces of the living code that nature has been perfecting over billions of years. The idea that life might operate according to a holographic principle is equally fascinating. Every part of the system contains information about the whole. In biology, this is seen in the way each cell of a multicellular organism carries the complete genome, even if it only expresses a fraction of it according to its specific function. Even simple molecules such as glucose reveal this triple nature. They are matter, they provide energy, and they transmit metabolic information that regulates cellular activity. In a profound sense, every biochemical flow is also a flow of information, encoded in concentrations, gradients, and molecular signals. This vision recalls the ancient idea of Aristotle, who in his treatise De Partibus Animalium spoke of form and matter as two inseparable aspects of reality. For him, the soul was the form of the living body. For Faggin, living information is that dynamic form, an ongoing choreography between structure, energy, and meaning. Understanding this hidden language of matter is not only a scientific challenge, but also a gateway to a broader comprehension of life itself, a comprehension that, according to Faggin, could redefine the very limits of what we call intelligence. And perhaps the most profound implication lies in how we view ourselves. If living information is inseparable from matter and energy, then our thoughts, emotions, and choices are not detached abstractions, but embodied processes woven into the very fabric of existence. This recognition dissolves the false boundary between mind and body, showing us that our consciousness is not floating above biology, but emerging from within it. In this light, every breath, every cell, every heartbeat is both matter and meaning, both energy and awareness. Such a perspective does not diminish humanity. It expands it, inviting us to see intelligence not as something we possess, but as something we participate in, an intelligence that is cosmic, cellular, and deeply alive. In popular imagination, we often compare the human mind to a computer and the body to a biological machine. For Faggin, this analogy is profoundly mistaken. Although it may serve as a superficial metaphor, the differences between living organisms and artificial systems are so vast that the comparison collapses under serious examination. In a computer, hardware and software are distinct entities. Programs can be installed, modified, or deleted without physically altering the structure of the device. In contrast, in a living being, the programming is inscribed into matter itself. DNA not only carries instructions, but also forms part of the very mechanisms that execute them. Information, matter, and energy are inseparable. Every cell is at once the medium and the interpreter of its own code. This integration grants life capabilities that current technology cannot match. An organism can repair itself. A cut on the skin immediately triggers a cascade of processes that regenerate tissue. Machines, on the other hand, require external intervention. No computer can heal a burnt-out microchip on its own. Life can also reproduce and transmit its characteristics to future generations, something unthinkable in a system designed by humans. A server may clone data, but it cannot build itself from scratch or adapt spontaneously to a changing environment. Biological metabolism is another demonstration of adaptive superiority. Glucose, for instance, is far more than just fuel. It is matter that builds tissue, energy that powers reactions, and a carrier of information that regulates cellular activity. The concentration of glucose in the blood can activate or inhibit metabolic pathways, adjusting the organism's behavior in real time. In a computer, energy resources do not transmit information or remodel its internal architecture. Faggin emphasizes that even the learning process in living beings is inseparable from its material substrate. There is no RAM detached from the processor. Experience is physically inscribed into synaptic connections, altering the very structure of the brain. This contrasts sharply with artificial learning, which modifies stored data without altering the physical nature of the hardware. Moreover, organisms display dynamic resilience. They can continue to function even when parts of their structure are lost. A plant can regenerate branches and leaves after pruning. An animal can heal deep wounds. One striking example of biological superiority is the way organisms respond to injury at multiple levels simultaneously. When a human body suffers trauma, for instance, not only does tissue begin to regenerate, but the immune system mobilizes, hormones adjust, and neural pathways reconfigure to protect and restore balance. This multi-layered response is astonishingly coordinated, showing that information, energy, and matter flow together seamlessly. No artificial machine today can replicate this orchestration. At best, we design separate subsystems that require manual intervention, whereas life demonstrates unity through spontaneous coherence. If a critical component in a computer burns out, the machine ceases to function immediately. The fundamental difference, according to Faggin, is that life does not merely process information, it lives within it. Living information is self-organized, self-referential, and evolutionary. It is not encoded in a passive medium, but in active matter that participates in its own interpretation. Human fascination with creating machines that imitate life goes back centuries, yet so far all imitations have been mere shadows. Artificial intelligence may emulate reasoning patterns or recognition tasks, but it lacks metabolism, lacks a body, and lacks the ability to transform itself in order to survive. For Faggin, recognizing this gap also points towards the direction science should take. Rather than attempting to reduce life to algorithms, future technologies might be better served by studying how living systems integrate resilience, adaptability, and meaning. Biotechnologies already hint at this potential, from regenerative medicine inspired by stem cells to materials that mimic self-healing processes. Yet even these advances are fragments compared to the totality of living intelligence. The true challenge is not creating artificial life, but learning how to align human creativity with the wisdom already inscribed in nature. For Faggin, understanding this gap is not a philosophical luxury, but a compass for the future. Technology can learn from biology, but it will never replace it, because the essence of life resides in that indivisible fusion of hardware, software, energy, and matter. When it comes to life, Faggin insists that it is not a mere reaction to stimuli, but a continuous process of anticipation. Every living being, from a bacterium to a human being, exists within a cycle of predictions and corrections. It does not simply record what happens. It tries to foresee what will occur and adjusts its behavior in order to increase its chances of success. At the heart of this process lie the models of reality that organisms build from experience. An animal that has learned where to find food does not need to wander randomly each time. Its memory and recognition abilities reduce uncertainty. Similarly, a plant adjusts its growth to reach towards the light based on a constant calculation about the most favorable direction. Learning arises from the continuous comparison between what was expected and what actually occurs. When prediction fails, the discrepancy acts as an error signal that pushes the internal model to change. This mechanism is not exclusive to complex brains. Even simple biological systems adjust their behavior when the environment shifts. At a deeper level, DNA can be seen as a record of successful predictions accumulated across evolution. Every trait that helps an organism survive is the outcome of countless trials and errors carried out by generations before. Genes, in this sense, are wagers that nature has placed on what will work in a given environment. The comparison with algorithms is unavoidable. Artificial intelligence systems also refine internal models by learning from errors, but their reach and flexibility remain limited. A chess program may learn to win games by optimizing moves, but outside that narrow context, it lacks common sense, intuition, or the ability to transfer its knowledge to entirely different problems. Humans, by contrast, can transfer lessons from one field to another. A sailor who understands how to read ocean currents may apply similar principles when interpreting weather patterns. This capacity for generalization is one of the greatest advantages of biological intelligence. Faggin highlights curiosity as the driving force of prediction. While an AI needs to be programmed to explore, living beings feel an intrinsic pull towards the new. Curiosity not only expands knowledge, but also builds resilience. By exposing itself to unfamiliar situations, the organism enriches its repertoire of responses for the future. Curiosity, in this light, can be seen as more than a psychological trait. It is an evolutionary strategy embedded in the very fabric of life. When children ask endless questions, or when animals investigate new environments, they are not merely satisfying idle impulses. They are building adaptive maps of the unknown. Each exploration adds to the organism's capacity to deal with uncertainty. Without curiosity, survival narrows to repetition. With it, life multiplies its chances by stepping into possibility. The essential difference, according to Faggin, is that human models are not mere statistical calculations. They incorporate emotions, contexts, and meanings that filter how experience is interpreted. Prediction is not only about calculating probabilities, it is also about imagining scenarios, assigning them value, and making choices accordingly. In nature, predicting well means living. A predator that miscalculates the timing of an attack loses energy. A prey that underestimates danger loses its life. This constant pressure has refined anticipatory strategies over millions of years, making them one of the pillars of survival. This principle, Faggin suggests, is equally vital for human societies. Communities that foster exploration, creativity, and learning from mistakes thrive, while those that suppress inquiry stagnate. Just as organisms refine predictions through trial and error, cultures evolve by testing ideas and embracing novelty. Education, therefore, should not only transmit fixed knowledge, but also cultivate the courage to question and the freedom to imagine alternatives. In this way, prediction becomes not just survival, but growth and transformation. Understanding this art of predicting and learning, Faggin claims, is not only key to understanding biology, but also to designing technologies that can integrate more harmoniously with life. For Faggin, human language is one of the most extraordinary achievements of evolution. It did not appear out of nowhere. Before words existed, our ancestors communicated through gestures, postures, and facial expressions. The gestural origin of language left a profound mark on our present-day communication. Even now, when we speak, we accompany our phrases with hand movements, changes in gaze, and micro-expressions that convey nuances impossible to capture in plain text. Over time, those gestures combined with articulated sounds, giving birth to spoken language, a medium capable of transmitting information more richly and precisely than purely gestural communication. The invention of writing marked a qualitative leap. For the first time, words could be preserved beyond the fleeting instant of conversation, able to cross distances and defy time. Yet this advance brought with it an inevitable loss. Writing froze the voice and gestures, leaving out much of the original emotional weight. This is where prosody comes into play, that set of elements such as tone, rhythm, and intonation that shape the meaning of what we say. Prosody carries emotional information that enriches or even alters the literal meaning of words. An "I'm fine" spoken with a trembling voice conveys something entirely different from the same "I'm fine" uttered with firmness. When we move from speech to writing, this layer of information is muted or disappears altogether, unless supplemented with descriptions or additional signs. Faggin proposes a fascinating analogy. The letters of the alphabet are like atoms. In isolation, neither letters nor atoms have any special meaning, but when combined into more complex structures, words in one case, molecules in the other, a new reality emerges with its own properties. The sense of language does not reside in the letters, just as the taste of water is not found in hydrogen or oxygen on their own. This parallel also highlights a crucial limit of artificial intelligence. Machines can process letters, words, and sentences with statistical precision, but they lack the lived experience that allows them to grasp their deeper meaning. An AI system may recognize patterns and predict likely words in a sentence, but without vital context, it cannot know what it is to be sad, excited, or hopeful. Human contextual understanding goes far beyond the linguistic. It draws upon memories, sensory perceptions, emotions, and expectations, all integrated simultaneously. This is why a phrase that may seem neutral to an AI can, for a human, be a message charged with history and significance. Faggin warns that even if we train models to imitate human language ever more closely, we must not confuse imitation with authentic understanding. True communication takes place when a message is not only decoded, but lived and interpreted in the light of shared experience. Ultimately, the true power of language does not lie in its symbols, but in its unifying force, the ability to connect minds and to transmit not only data, but meanings, feelings, and entire worldviews. This, Faggin insists, is something no machine has yet managed to replicate, and perhaps this is the heart of the matter. Language is not a tool we merely use, it is a mirror of our consciousness. Each word we speak carries echoes of our biology, our history, and our imagination. In dialogue, we do not just exchange information, we shape one another's perception of reality itself. This creative force, subtle, invisible, but deeply transformative, is why language remains one of the most powerful gifts of being human. This perspective also challenges us to reflect on our digital age. Every day, billions of words are exchanged through messages and posts, yet without the tone, gestures, or living presence that give them depth. Faggin reminds us that while technology multiplies our voices, it also risks flattening their meaning. To communicate fully, we must recover the human dimension that gives language its soul. For Faggin, any serious attempt to understand the universe must go beyond the mere accumulation of data or mathematical formulas. Modern physics has indeed managed to describe with astonishing precision the behavior of matter and energy, but it still leaves one essential question unanswered. What does it all mean? One of the most influential visions in this respect was that of John Archibald Wheeler, who proposed the idea of it from bit, the notion that all physical reality ultimately arises from binary information. According to Wheeler, what we call things, particles, fields, galaxies, are nothing more than responses to questions asked in the language of physics. In his conception, the universe resembles a gigantic cosmic conversation in which information precedes matter. Faggin acknowledges the power of this idea, but also warns of its limits. It from bit may describe the structure of physical reality, but it does not explain how, from that information, subjective experience emerges. Here lies the core of his critique of dualism. Radically separating the physical from the conscious is, for him, a mistake of perspective. The mind is not an external observer that merely receives data from an inert universe. It is part of the same fabric of reality. In the field of computation, quantum physics has opened fascinating paths. Qubits, the basic units of quantum information, are not restricted to the states of 0 or 1, but can exist in a superposition of both. The block sphere is the visual representation of this flexibility. Every point on its surface corresponds to a possible quantum state of a qubit. This allows calculations that, in certain cases, would vastly surpass those of classical computers. However, Faggin stresses that even quantum computation has clear boundaries. No matter how powerful these devices may become at solving optimization or simulation problems, they do not possess free will or genuine creativity. Their operation remains determined by algorithms designed by humans. There is no inner spark generating new meanings without prior foundations. To make this more tangible, Faggin often invites us to consider how physics itself emerged historically. Equations did not fall from the sky. They were the product of human minds searching for patterns in their lived experience. Behind every formula lies the intuition of a thinker, an act of consciousness trying to describe what was already felt as meaningful. In this way, even the so-called objective language of science is inseparable from the subjectivity that gives it birth. This is where the contributions of physicist Giuseppe Dariano come into play. He has proposed a framework in which the laws of physics can be derived from purely informational principles. Dariano suggests that the fabric of reality could be described without resorting to particles or fields, but rather as a set of informational processes interwoven with one another. Faggin values this proposal, but insists that even if physics were to be formulated entirely in terms of information, the leap from data to meaning would remain a mystery, one that only consciousness seems able to resolve. This reflection also highlights a hidden danger in our fascination with information. In an age where data flows faster than ever, we risk confusing quantity with depth, precision with wisdom. Faggin reminds us that information without consciousness is like ink without a reader, marks on a page that remain inert. It is only when a living being encounters the sign that meaning arises, and with it the possibility of transformation and understanding. This approach leads to an inevitable question. If everything is information, where and how does meaning arise? For Faggin, the answer points to consciousness being a fundamental component of the universe, not merely a byproduct of physical processes. Just as light and space-time form part of the basic structure of reality, so too would the capacity to experience and to endow reality with meaning. Physics alone cannot answer the whole of this question, because it works with objective models. Consciousness introduces a subjective dimension that resists being encapsulated within equations. The paradox is that although meaning is precisely what we seek, it can only truly be found through participation in lived experience itself. Faggin closes his reflection with a provocative image: to imagine the universe as a great unfinished narrative in which each conscious being writes a part of the story. Atoms and galaxies form the stage. Information is the language, but the meaning, he affirms, is the trace left by each consciousness as it lives. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.